So, next part is your constant head method to determine coefficient of permeability. As I said last class, so there are two methods, one is your constant head method, other is your variable head method. In this method generally you add water and collect at the outflow when the rate becomes constant. That means, how do you know that? Add water until it is hydraulic gradient become 1, that means rate becomes constant, that means you collect water in a stipulated time. So, same water you are getting a regular time interval, then you can say that the rate becomes constant. So, at that conditions you find it out what is the difference coefficient of permeability of soil. If you look at these constant head apertures, generally what happen, there is a soil and water has been allowed to flow through the soil in a constant head, that means this head is fixed, this height of the water fixed from the soil, so that the head is fixed. So, water allows to pass through the soil. So, then you will collect amount of water in the outflow passing through the outflow. Water discharge per time, based on the time you can find it out your coefficient of permeability. So, L is the length through the soil. If you look at here, means water passing through the soil from here to here, this is called length. Y is the height of ponded water, that means height of the water above the soil. X is the height of water required to lower the gradient, so that Y can be maintained. X is the height of the water required to be lowered, so that Y should be always maintained. If gradient is 1, then Ks is equal to Q as per Darcy's law. Now, come back to falling head method. In this falling head method, weight the column from the bottom up, fill a burette to above the height of the soil column and allow it to drain. Drain until rate of head loss is constant, means rate of head loss is constant. So, coefficient of permeability of soil, you can find it out AL by A into T2 minus T1 log S2 by H1. It is called falling head, that means the head has to vary. Where this falling head has been used, this falling head used for the soil of fine grained soil generally. For constant head method has been used to find it out coefficient of permeability of coarse grained soil. Now, if you look at this falling head apertures, this is soil. So, this is a burette, water is there, means initially you pour water inside the burette, then A is your diameter of the burette, and find it out what is your time interval time T1, then after certain height S2 you find it out time T2, L is your length of the soil where it is passing through. Now, area of cross section, the moment I say area of the cross section, if this is my soil sample, how water flow through this, water is flowing through this in this direction or in these directions. That means, this is the area of cross section through which water passes. So, A is your area of cross section. If you know the change in water collected with your time T1 as well as T2, and these are your fixed parameter, that means A is your diameter of burette, cross sectional area of soil you know, length of the soil you know, in that mold what is that length of the soil that you know. Then if you collect the outflow, that means discharge with respect to time T1 and T2, then only you can find it out what is your coefficient of permeability for falling head apertures, that means for fine grained soil. If you look at A is your diameter of burette, L is your length of the soil specimen, A is your area of cross section, T2 minus T1 with this time T2 and T1, and S2 by H1 is nothing but your head or height. If you look at here, H1 with time T1 with time T2 with this, what is your head? This is your S2. From there you can find it out coefficient of permeability by means of falling head method. This is I explained now. Another one is called test basin method. That means isolate a column of soil, usually much larger than a core to be used in the laboratory. Seal the lateral faces of the column, ensure the column is saturated, apply a constant head of water at rate P, obtain Ks using a mass balance approach. That means I is equal to P minus E, where Ks is equal to I since soil is saturated. This is called test basin method. So, Ks, finding out coefficient of permeability of soil, the constant head method is used for soil with a height with a high Ks, means high coefficient of permeability. That means the soil whose coefficient of permeability is greater than 0.001 cm per second, 0.001 cm per second. That means high coefficient of permeability. From where you will get it? You will get it for cohesionless soil, high coefficient of permeability, because these are sandy soils where you are going to or you are expecting high coefficient of permeability. The range is given if K's coefficient of permeability of soil is greater than 0.001 cm per second, then constant head method is to be used. Somewhere else coefficient of permeability is written K, some people they write it Ks, some will write capital K. So, it depends upon the notations how they are using. The falling head method is used for soil with lower permeability. That means, if coefficient of permeability is varying between 10 to the power minus 3 to 10 to the power minus 6 cm per second, that means this is for your fine grained soil, then the falling head method to be used. Falling head method indirectly it says that it is for fine grained soil. This is for coarse grained soil. Laboratory experiment can obtain Ks in each dimensions, both the dimensions you can find it out, means coefficient of permeability. Before I start this determining this unsaturated K, now if you look at here, this Darcy's law saturated flow, vertical or horizontal, if I go back to theory, volume of discharge rate Q is proportional to head difference dH and to the cross sectional area A of the column, but is inversely proportional to the distance dl or L, we say L or dl or H or dH of the flow path, and coefficient of permeability K is called coefficient of permeability or coefficient of means conductivity, sometimes hydraulic conductivity of soil, let us say, is Q is equal to minus K delta H by L. The average flux can be obtained by dividing Q with A. The flux is often called Darcy's flux QW, Darcy's flux QW. Now, if you look at these estimated methods, grain size, very fine sand or poorly sorted, means it will be 40 to 80%, means applicability sand sediments. So, K is equal to C into 10 D10 square. D10 is your grain diameter for which 10% of distribution is finer. That means, effective grain size where D10 is between 0.1 and 0.3 centimeter. C is a factor that depends upon grain size and shortening. C is a factor, and medium sand well graded, these are all tabulated form, it is given. Field testing, if you look at this field testing, this is called borehole permeameter. One of the testing, as I said earlier, in the field permeability, how do you find it out? One is method is your pumping in, pumping out, other is your by means of tracer, third is your by means of borehole method. And this is one of the field test, that is called borehole permeameter or permeability test. If you look at here, these are all testing arrangements of the field testing for borehole, you see 12 inch to 6 inch double ring has to be provided here, and by means of borehole constant or falling head permeameter you can measure. If I go back to my this double ring infiltrometer is a central valve with this infiltrometer principle is as per this cylinder of 30 centimeter in diameter. Smaller rings are available also. Drive 5 centimeter or more into soil structure or horizon. Water is ponded above the surface, typically less than 6 inch. Record volume of water added with time to maintain a constant head. How much of volume of water required to maintain a constant head? It can measure a combination of horizontal as well as vertical flow. This is a single ring infiltrometer. So, you in that infiltrometer allow water, so measure the volume of water with time to maintain the constant head. That means equal amount of water passes through this borehole with equal time difference at where it will achieve a constant head. That means how much volume of water required to achieve your constant head. That is in case of this both single as well as double ring infiltrometer. This advantage is this, by borehole method you can measure both a combination of horizontal as well as vertical flow in case of in field testing method or in situ conditions. Now, ASTM double infiltrometer means, if you look at this ASTM double infiltrometer, this is your infiltrometer and outer ring are means particularly this is your outer ring. This outer ring is about 6 to 24 inch in diameter and ASTM recommend 12 to 24 inches, and Marriott bottle can be used to maintain constant head. This is a bottle to be used to maintain constant head, and the rings driven 5 centimeter to 6 inch in the soil and if necessary to be sealed. Basically, in this ring what will happen, it should be inserted inside the soil and from here water should be added to the ring. So, it allowed to flow through this. Once it allow flow through this, then you can find it out how much water passed through the soil in equal interval of time, so that a constant head has to be measured means maintained. Once a constant head has been maintained, then you can find it out what is your coefficient of permeability. So, particularly very difficult to install and seal ASTM double rings. Single rings are easy to install and easy to seal, particularly very difficult in double ring, because this entire has to go inside, because this is pipeline from where there. But in case of single ring, there is nothing, you can add water from the top. You see, significant effort is needed to seal install and seal units. That means ASTM requires documentation of depth of wetting front. There might be a chance of leakage here, potential leaking area, here may be leaking, here may be leaking, it has to be sealed by means of bentonite slurry. Other double ring small diameter are easier to install or repeat the testing. This is a 6 inch to 12 inch double ring, 3 inch to 5 inch double ring in 12 inch diameter. Look at this, how it has been installed. Means these are all your infiltration data of this test has been made by Oram 2005. Now, come back to this field test. Look at this, by means of boring, in situ boring method, means this is your borehole, you made the borehole here and boring pipe has been inserted here. By means of single rig 12 inch to or 6 inch or single ring or double ring, you allow water to flow inside, so that a constant head has to be achieved. Once a constant head has to be achieved, that means delta H by delta L amount of soil where you are considering inside this borehole. With the time you can find it out your coefficient of permeability in situ, vertical as well as also laterally. Another one is it has a different permeameter. You see sometimes it is given naming Talsma permeameter, where you see here you have modified Amundsen. So, here water you add it, how much water passed through this you can find it out. So, this is a constant head borehole permeameter. What is delta H? If you look at delta H is, if you look at the total hydraulic head at inflow, at point of inflow total hydraulic head is your at this point total hydraulic head is, if it is HI, that means HI rho plus HJP. What is HI rho? Means if you look at here, this is your length of the soil plus this is your water. So, datum plane placed at the outflow, that means where this outflow will be there, datum plane has to be placed it. This is my datum plane. So, total hydraulic head at outflow H0 is equal to 0, because datum plane has been placed here. So, delta H change in hydraulic head is HI minus H0. HI is nothing but your, it has come from here, soil with water minus O. So, this will, so hydraulic gradient I is equal to change in hydraulic head by length. So, this is your change in hydraulic head and this is your length. Borehole permeability testing can be a suitable method. Falling head and constant head method may be suitable. Permeability data for specific sites should be calculated using geometric average. Means specific data, specific site, permeability data, suppose specific site is, this site is there. So, how do you find it out? In geometric average, you consider one borehole here, find it out permeability, one borehole here, find it out permeability, one borehole here, find it out permeability, one borehole here, find it out the permeability. With this, once you find it at the permeability, then you can take its average. Equations and methods based on Darcy's law, and the result is a value for K or Q. Always do not recommend estimating permeability based on particle size distribution, do not recommend it. Laboratory permeability testing is also possible, but it may be difficult to get a representative sample and account for induced changes. So, best is you go for borehole permeability testing in the field in situ condition, then you record it on that site, record it 3-4 places and take this average. This average value has to be reported to find it out, means particularly this geometric average value of this K has to be reported for your final value of coefficient of permeability of soil. Let me start with this aquifer testing, laboratory permeability test and field test. After this borehole test, field test also, pumping test also, slog test also remaining. So, let me finish, then I will go to that. Means as I said, as I discussed last class, in laboratory permeability test it involves pouring water through the column of soil and measuring flow rate, and you should get undisturbed sample for the test to relate the field condition. Undisturbed sample of the soil column you have to collect from the field, so that whatever permeability in the laboratory you are going to get, it has to be correlated to the field condition. Laboratory permeability test, as I said, with your constant head K is equal to QL by AH. So, Q is your discharge, L is your length, A is your area of cross section, H is equal to head causing the flow. If I make it into Q, total Q into L, A into H into T. So, Q is your total volume of water and T is the time period required to cause the head causing flow, and L is your length of the soil specimen. As I said, A is your cross sectional area. Now, constant head method, just a bigger picture I want to show this. This water tank has been placed above the soil sample. Earlier just I saw this, means what is the principle, how it has been done. This is the laboratory test equipment. Now, the soil sample has been put inside a mold. It cannot stand inside a mold. With this mold, if you look at this, top part is connected with porous also bottom part is connected with this, you can connect means place your porous stone both at the top and bottom, and here it is your porous stone or porous disc. Why porous disc? The moment you allow water, only porous stones are only allow water to pass. That means the moment water is here, it passes through top of the soil sample. So, water is allowed to pass through the porous stone along the soil sample. Then at the bottom what will happen, porous stone will only allow water to flow, not allow soil sample to flow through here. So, this is mold, inside this mold your soil sample is there, and with this soil sample connect it by means of piezometer. So, you can find it out how much is your hydraulic head developed, H prime how much is your hydraulic head developed. Then here at this here there is a graduated jar is there, from there you collect your water. Basically if a constant head permeability, this is your constant head permeability method, what will happen, water first you allow from the tank, it should be placed over the soil, so that the head has to be maintained. So, water will pass inside. So, how water will pass? Water will flow from higher head to lower head. So, head loss or head with a differentiated head you will observe by means of piezometer. This piezometer will be at the top. So, how much water will be here, you can find it out, this is your water. This is piezometer at the bottom of the soil sample, you will find it out water level here. With this water level top and bottom, then you can find it out H prime, what is your head loss, and with this help of head loss you will find it out constant head permeability, you can find it out what is your coefficient of permeability. You see sometimes we write K, sometimes some people write K. So, K earlier slides are Ks, here it is K, it is nothing but coefficient of permeability. Now, this total volume of water, can you measure it, how much volume passing through this? Yes, I can measure. How we will measure? Look at here, the moment you allow water to pass through this here and collected in a graduated jar, that means you take a stopwatch, allow for suppose say time t is equal to 1 minute. Initially you start time t is equal to 1 minute. Then with this stopwatch take time t is equal to 4 minute. With 4 minute time t interval collect the water, how much water you are collecting. Then second step, with time you start t is equal to 4 minute, then allow another time interval say 4 minute, that means next step of 4 minute plus 4 minute, at 8 minute time then you collect your water and stop the collection of water, means at regular interval of time how much water collected that you can measure. From there you can find it out your discharge or total volume of water where it has been collected in this graduated or measuring jar, how much amount of volume of water you can collect, you can find it out. Then head causing the flow, you can find it out from here by means of measuring the piezometer, you can find it out head causing the flow. Then time period, how much time period, as I said initial time, so t1 is equal to, so say 0, t2 is equal to 2 minutes, how much time period? With this 2 minute of time period of time you have collected discharge of this ml, say 10 ml, with 2 minute time interval you get the discharge, say q is equal to 10 ml, and time interval t is equal to with 2 minutes, that means you will get q, you will get t, h you will find it out, as I said h you will get it from here, what is your hydraulic head, from there you can find it out h. So, h you also you get, you know length of the soil sample, from the mold you can know what is that pre-decided length, means this is your fixed length, what is your length you know it. So, once you know the length, then what else remaining, area of cross section, that you can very easily find it out, from there you can find it out coefficient of permeability by means of constant head permeability, you can find it out. So, this is means earlier slides are how it has been done, what is the physics behind it, and this slide is showing coefficient of permeability by constant head method, laboratory equipment, and how this laboratory equipment has been placed for this coefficient of permeability by means of constant head method. Now, come to next, what are the measurement you are going to do? This is your calculation sheet. That means mass of empty mold with base plate you measure. You have to take at least 3 molds, so that average value, as I said, one coefficient of permeability may not be correct. At least 2 to 3, at least 3 mold you will take it, or 3 soil sample you will take it, find it out coefficient of permeability and take the average. So, initially mass of empty mold with base plate you measure, mass of mold with soil and base plate you can find it out. Third is your hydraulic head, you can get it. Then time interval, quantity of flow you can get it. So, first time in period T, second time in period T, third time period in T. What do you mean by first time period in T? Suppose with first time period of 2 minutes, what is your flow? What is the Q? Means how much water you collected in the measuring jar. Second time period, suppose say another 2 minutes, how much volume of water you collected, how much ml you are collected. Suppose first 2 minutes you collected 10 ml, second 2 minutes you collected 8 ml, third you collected suppose say 12 ml. That means average value of 10 plus 8 plus 12 by 3, this QL has to be reported, this average volume has to be reported. Do not go by only one value of Q, only one time interval, whatever you are getting the Q, that is not to be true, because inside the soil to get this, achieve this constant head, it takes time. So, what will happen? You take any 2-3 interval of time and take the average and report it for your calculations. So, from these, from 2 and 1, mass of mold, soil and base plate, if I deduct mass of empty mold with base plate, I can find it out what is my mass of the soil. So, mass of the soil you can get it 2 minus 1. So, bulk density you can find it out mass per volume, because mole volume is fixed 1 meter by 1 meter by 1 meter, means what is the dimension is there, it is fixed. Now, water content you can measure it, from this bulk density you can find it out dry density, then you can find it out also void ratio, what is the void ratio, it is also required. Then from all this value of Q, average value of Q, report it, length of the sample, length of the mold you know, area of cross section, hydraulic head and time interval. From there you find it out, this is your K1, this is your K2, this is your K3 for 3 soil samples. With help of K1, K2 and K3, then 3 permeability you are getting. Theoretically they are supposed to be same, but it is not true. So, the value will be means the value will be vary slightly, then you consider report it average value of the K1, K2, K3. This you have to report, means while reporting this, because this is a laboratory test, this is a laboratory test, more the number of samples you are going to test it, more accurate data you will get it, more average value you can interpret it. This is the same thing. The coefficient of permeability is the dimension is either centimeter per second or ml per second. If you look at this, it is a centimeter per second or mm per second, it depend upon that how you are representing this sample. Now, there are 2 tests, as I said, I have shown you just one detailed data sheet about the laboratory test data sheet, what are the measurement you are going to do 1, 2, 3, how many samples, what detailed data sheets, what you are going to get. Same data sheet can be used for variable head. In this variable head, this hydraulic head to be 2, H1 and H2 with time T1 and T2, these 2 things will come here. Then calculation as per the formula you can find it out what is the value of Q, and then you can find it out what is the value of K from this formula once you are getting. Now, this field test, this is your pumping test, pumping well installed in aquifer, observation wells installed at set distance from pumping well. Look at this, there are 2 tests I left earlier, borehole method I said, one is called, another method is called pumping in or pumping out test. So, pumping wells, that means pumping wells should be installed in a aquifer. There are two pumping wells, one pumping well has to be installed in aquifer, other pumping well is called observation well. It should be installed at a certain distance away from your pumping well. Pairs at right angle to test for anisotropic. If this is my pumping well, means pairs at right angle. So, one pumping well will be here, one will be here. So, that it should be right angle to each other, so that I can find it out anisotropic. Anisotropy means isotropic anisotropy. Anisotropy means the property of permeability in x and y direction, it should not be same. Isotropic means kx is equal to ky is equal to kz. X, y and z direction the permeability is same. Pumping several hours to days at a constant measure rate. That means pumping means you pump it constant rate. That means several hours to days. It may be 4 hours, it may be 8 hours, it may be 1 day, it may be continuous 2 to 3 days at a constant measure rate. At a constant measure rate means you decide how much amount of water to be pumped out, how much water, say suppose say 100 ml of water. So, maybe 1000 ml of water, that is called constant measure rate, that measure rate should be constant. Pumping causes drawdown in pumping well. The moment you start pumping water outside the pumping well, if this is a pumping well, the water level is here, then you are pump out, so sudden drawdown, the water level will be fall down. And manual and electronic water level measurements before, during and after pumping. That means both manually you can measure it. Manually how you can measure it? You place a scale from top to bottom, you place a scale. Suppose this is started with 0, this is your 100 mm. So, how much height water you have pumped, that you can measure by manually or by electronics device. Electronics device you can place it, it can directly give, once the dimension is fixed, you know the how much volume of water is there. So, how much has been pumping out, that you can electronically you can measure it. You place it so meticulously, so that you can measure before what is the height, and during also what is the height, and after the pumping how much the height has to be achieved. Drawdown recorded at pumping well and observation well, both these wells you measure how much drawdown has been achieved. So, another test is your, this I am going to show you also in details, these are all in field, I am going to show you in details. If you look at here, this is your aquifer, means water table is there, water level is there, aquifer. In that aquifer means this is constant aquifer, in that case you just a discharge well, this is your discharge well, and nearby at certain distance, you know this distance, with this distance this is your observed well, either one well or two wells you can put it. So, what will happen, at a constant rate this discharge you pump, at a constant rate you take out this water from this aquifer. So, what will happen, there will be a sudden drawdown of water. So, how much of water from the soil, it is a sudden drawdown, with this observed well and as well as here you can measure it. This is how this physics, how it looks. If I summarize how it looks outside, if I draw a schematic diagram how it looks, but in the field it is different. You see how this pumping in, pumping out, pumping test has been done. If I take it here, pumping test monitoring this observation well, these are my observation well 1, observation well 2, it has been electronically pushed, so that you can find it out what is your observation wells also. Then you see this by means of tape also you allow the tape should go inside, you can measure the how much of height of fall, what is the distance, the water drawdown is there. You see how much pumping means, by means of constant rate you are taking out the water from the aquifer. These are pumping test heavy equipments used in the field, means sometimes some people use heavy equipment, sometimes some people are using portable equipment. So, then we will go back to our next part of this sludge test, that I will discuss in the next class.